Okay, so what we're looking at here is something called a series RC circuit. So we call it that because it has some resistance, which is R, and also some capacitance, which is C. Pretty common way for these to be presented, where you're given the supply voltage and the supply frequency, and you have to calculate capacitive reactance, impedance, and the current. Just keep in mind that it is also quite common to be asked to simply calculate the current for one of these, but you just got to understand that we can't simply go to that step. We need to do steps A and B before we can get there. So let's start with A, which is working out capacitive reactance. Okay, so if you're not sure why this is important, well, in AC theory, we need to know for every single component that we deal with, the degree to which it opposes current. It's very easy for a resistor because that 80 ohms that we're shown in the questionnaire, that is the degree to which it opposes current. But for the capacitor, that value of 24 microfarads, even though that is very important in some regards, it doesn't tell us the degree to which that component opposes current. So we need to work out the capacitive reactance, which is what that is. So our formula for capacitive reactance, XC is equal to 1 over 2 times pi times the frequency of the circuit times the capacitance of that component. So if we step down and put some numbers in here, we're going to see that we have 1 over 2 times pi, that's always going to be the same. Multiply that by our circuit frequency of 50 Hertz. Multiply that by our capacitance, which is 24 microfarads. Just one thing to look out for here, that value is presented to us in microfarads. So we need, in order to use it for our equation, we need to convert that from microfarads into farads. So the way we're going to do that is we take that number of 24 and we're going to multiply it by 10 to the power of -6. What that's going to do, remember, is essentially move the decimal point 6 places to the left. And that's going to convert that from microfarads into farads, which is what we need, because we always have to put numbers in base. So if we put those into the calculator, we see that we get a capacitive reactance of 132.63 ohms. Okay, so just a couple of things there. I've rounded that number for the sake of this exercise, which is okay, but just keep in mind that the more times you round numbers along the way, essentially the less accurate your answer might be at the end. Also, always include the unit there, which will help you if you're referring to this later on. Okay, so let's take that capacitive reactance. I'll just write it underneath the question here. Okay, that's our answer to A. I'll just have to take this off the board to make a bit of space. We're going to look at impedance. Question B. Okay, so impedance. Now, if you're not sure why that's important, well, we can think of impedance in an AC circuit as the total opposition to current flow. So again, if a circuit simply just had resistance in it, then that resistance would be the total opposition to current flow. Or if this circuit simply had a capacitor only, then the total opposition to current flow would be capacitive reactance. But as soon as we have a combination of resistance and, say, a capacitor in this case, then we need to work out the impedance. That's the total opposition to current. So for a series circuit, the way we do that, we can draw ourselves what we call the impedance triangle. It's just a right angle triangle. We'll have an angle in there, which we'll talk about soon. That's what we call the phase angle. And we can label our sides of the triangle like this. So the horizontal adjacent side, that's always going to be the resistance. And we can just put our value of 80 ohms onto that side. the opposite side, or the vertical component of this, that's always going to be your reactive component. So we tend to symbolize reactance with an X, and in this case it's capacitive reactance, so I'm going to write XC. And we can pop onto that side of our triangle that capacitive reactance that we actually just calculated, 132.63. Cool, so now that we've labelled the sides of the triangle that we know, it's going to be this side, the hypotenuse, which is our impedance. So that's going to be our total opposition to current. Hopefully, if you know a thing or two about Pythagoras, you can find this pretty easy, where we can just simply solve that remaining side. So to do that, we'll go, okay, impedance, straight up Pythagoras, where we go R squared plus, in this case, capacitive reactance squared. Plug your values in, 80 ohms plus 132.63, both of those squared, of course, and we get an impedance of 154.89 ohms. There you go. So again, just remember the unit that we're using here, any opposition to current flow, whether it be resistance, capacitive reactance, inductive reactance, or impedance, they're all going to be measured in ohms. So again, I'll take that value, pop it over here underneath the question. Cool. All right, so I'll just make some more space here. And we'll tackle question C, which is working out the circuit current. Might just leave that triangle there, or park that there, because it could be useful later on. Okay, so C, working out the current. So now we've got to understand that most times in AC theory, to work out the current, not every time, but sometimes, we actually use some form of Ohm's law. So Ohm's law for current is always going to be the voltage divided by the opposition to current. So again, if we just had resistance here, then that would be R. If we just had capacitive reactance, then that would be XC. But because we have a combination of resistance and something else, in this case capacitance, it's going to mean that our total opposition to current flow is that value of impedance that we just calculated. So now it's pretty simple. Ohm's law, supply voltage is 230. Our impedance we've just worked out is 154.89 ohms. That's going to give us a value of current as 1.48 amps. There you go. Again, we'll take that value of current, pop it underneath the question. And there we have it. Okay, so that's all the question asked of us. But I just wanted to, while we're here and talking about it, take it a little bit of a step further and talk about this thing in here, which is what we call the phase angle. Because even though we've worked out the value of current here, we can dig a bit deeper and work out the phase angle, or the phase relationship between the supply voltage and this 1.48. Because due to that capacitive reactance in the circuit, it's going to mean that the voltage and the current essentially are not peaking or reaching their maximum values or crossing zero at the same time. So let's work out what that angle could be. So we'll just label this phase angle. You can see, because we've got the triangle there already, it's just a matter of us solving that angle in there. So if that's our angle of reference, we know that we've got the opposite side, and we've also got the adjacent side there. Of course, we subsequently solve what the other side of the triangle was, but let's use the opposite and the adjacent. Of course, if we think of SOHCAHTOA, opposite and adjacent, that's going to mean we're going to use the function of tan. So to solve that angle there, we'll go the phase angle, inverse tan. That's going to open up your brackets, put in the opposite side, divide that by the adjacent of 80. And if you do that correctly in the calculator, you get an angle of 58.9 degrees. So that's the phase angle. We can now even take it a step further, and if we understand what capacitance and therefore capacitive reactance does to a circuit, overall it's going to make the current lead the voltage. So we could say that the phase angle is 58.9 degrees with the current leading the voltage.